Can you give me some examples of algebraic thinking, that third level of functional thinking that you were talking about? I sure can. My name is Eric Normand, and I help people thrive with functional programming. So I got a question about an episode I did a week or two ago about the three levels of functional thinking. So the three levels were basically, the first level is just thinking in terms of actions, calculations, and data. Okay, so just kind of dealing with the fact that you've got immutable data, you want to separate your actions from your calculations, those kinds of things. Second level is start thinking in terms of data transformations and the pipelines, and you're using map, filter, reduce, those kinds of things to get the data that you have to look like the data that you need in a very high level, higher order function kind of way. The third level was what I was calling algebraic thinking. Algebra, you're creating an algebra to model your domain. And I got a question about this in a YouTube comment. It was from P1MPS01, not to be confused with P1MPS02, but P1MPS01 asks if I can give some examples so that it's clearer what I mean by this algebraic thinking. So I came up with 3 tidy little examples that I can talk about. So that's what we're going to do in this episode. So the first example is, imagine you're writing a video editor. I don't know if you've ever edited video, but if you have a GUI editor, you can put clips in and overlay the clips and like make transitions between things and cut stuff out. You can do all sorts of stuff. Now I want you to think for a moment how you might implement this. Okay. While I'm describing this algebra, you might see how this there's the technical details of how to actually put the video together, right? How to render that final video so that you can output it. You could put it on YouTube or whatever you do with your final video. What the algebraic thinking is about how do you represent that video before you've rendered it. You're representing it in memory in a way that you can manipulate and will also feed into whatever rendering engine you've got. Okay, so this is how I would begin to describe an algebra of video editing. So we have the notion of a clip. This is a video clip. Now, at heart, in the essence of the video clip, it's basically just a function from time to image. So you give it a time and it gives you an image, right? This will allow you to sample the video. This is more implementation details, but it will allow you to sample the video at whatever frame rate you need and get a frame out at whatever time you need for that frame rate. Okay? And so then we have to think about, how do we compose these things together? So there's really 2 main ways to compose clips together. One is in sequence. So when this one stops playing, we'll start playing that one, right? The other one is overlay. So this is if you want to put some text on top of a video, you can overlay that text on top, right? And so whatever you're deferring to the overlay of images. So you would ask for the frame at time t from video A, and B is on top of that, overlaid on top. So you'd also ask for the frame at time t of B, and you would overlay the images. And so we kind of defer to however our image system works. That's how we're gonna overlay the images, because overlaying in images is also, you could also think of that as an algebra, but we're not going over that. We're just going over these clips. Then there's also stuff like trimming, right? So you want to cut a sub clip from this clip, right? And you can actually break it into two operations. You can trim from the left and you can trim from the right, and you'll have something left in the middle, right? And with these operations, you can do basically anything you need to do with the video. Okay, there's going to be some things that are done more on the frames of the video. So for instance, you could transition, fade to black kind of thing. That would be done at the image level, but you need some way of representing that as part of this algebra, right? That this is a transformation, not on. So, okay, here's the thing. We're all playing with time here. Right? This is a function of time. The only input you have is time. Then you have the output, right? So the input you have is time. So when I take clip A and I take clip B and I sequence them so that B plays after A, I make a new clip. And that clip basically, when I ask for a frame at a certain time, it will, if it's less than the length of A, it will give me the frame from A. It'll ask the function A, what's your frame? If it's greater than the length of A, then it'll subtract the length of A from the time and use that time to pass to B, and it'll get a frame from that, right? So this is a very simple composition, a simple way to compose that doesn't require like complex math or, a real understanding of like video formats and things like that. It's simply a very easy implementation. It's either ask A or do a simple like subtraction and then ask B. Okay, so that allows us to compose these two things in sequence. And we've already seen what happens if I put B on top of A. We're going to ask A for its frame at that time, and we're going to ask B for its frame at that time. And then we're going to do whatever image overlay we have for those two frames. Now you can also see that we're going to have some issues where we have to solve, like, well, what if I want B to start later, like than A starts, right? I want to overlay B, but I don't want them to start at the same time. Well, you can make an empty video, an empty clip, right? That returns an image that's just transparent, right? And so then the overlay the overlaying a transparent on top of A is not going to change it, but it makes it start at the right time. You can sequence that empty clip, which has a length, you can sequence that empty clip with B, and it'll start at a later time. So you can see we can start to play with these primitives that we've made, and we've defined a formal way that they compose, and we've got basically everything we need from just these very small pieces. Okay, let's look at another similar, actually, algebra. This is parser combinators. Okay, so you can define a parser in terms of other parsers. This is known as parser combinators. So if you have some very primitive parsers, let's call them parsers, it takes an input stream, you could say it's a string, and the only thing it does is it looks for one character, and it succeeds if it finds that character, and it fails if it doesn't find that character right at the beginning. right? The first character of that string, it's going to compare. So you've got this very primitive, easy to implement operation. Now, how do you use those primitives to make a parser that parses something more complicated? Well, you have sequence. So you say, well, I have to match A, and then a B, and then a C, and then a D. But really, the sequence can work with only 2 parsers. So you take a parser that matches A, and you take a parser that matches B. You compose them into a parser that matches A, then B. Right? It's very, you could implement it very simply. You can already see how to do it. That first you match A on the string. If it succeeds, you drop the first character from the string, and then you try to match B on that new string. If that succeeds, you're done. If either of them fail, the whole thing fails, right? Very simple means of combining, right? All right, now that's not enough because you need some choice. What if I want to match A or B? Well, you need a thing called alternative, alt, something like that, that takes an A, and if A fails, then it tries B on the same string. It doesn't remove it. Okay, but if A does pass, if it succeeds, then it doesn't call the B, right? So in this way, you can compose up from these very primitive pieces an entire parser that will match certain strings, right? And this is like a context-free grammar that you can create. Notice it's got a lot of similarities with this video editing algebra. The video editing algebra had sequence. This one also has sequence. And notice that they're monoids. We went over this in another episode. Monoids are operations. They're binary operations that take 2 things of the same type, and the thing they return is of that same type too. Okay, so the 3 pieces, the 2 inputs and the 1 output, are all the same type. You take 2 parsers, you return a parser. You take 2 clips, you return a clip. It's a monoid. And the other thing about monoids is that the grouping doesn't matter. So the order of operations doesn't matter. You should look that up in past episodes. I just did one on the difference between associative and commutative. Monoids are associative, and they have an identity. So like the empty clip would be an identity. It doesn't do anything when you sequence. If you have a clip of 0 length and you sequence it with some other clip, it's just going to be the same result as that other clip. Same with the parser. If you sequence you could consider a parser that always passes and does not consume input. That's an identity for that sequence operation. Okay. So notice when we talk about monoids, that's something very useful when you're developing algebras, is to find these places where a well-known, well-understood, usually named algebraic concept matches what you're doing, right? So monoids are really easy and they're very powerful. So I often look for monoids when I'm doing this. But there's a lot of other algebraic properties as well. And this is where a lot of people find value in category theory when they're programming, because a lot of these things, these algebraic properties, were developed as part of category theory. Okay, I want to go over one more. This is the third example. This one is not a monoid as far as I can see. It's more like a little state machine, but it's modeling an asynchronous value. So this is a value stored on a server. And let's say you're on the browser, you're programming the browser, the front end, and there's a value on the server. And you need to get that value. But there's time between when you initiate the request and when the response finally comes back. And you want to model that somehow. You want to model that the request is in flight. Maybe you need to show that loading spinner. Often, if you kind of do it in like a jQuery way, you don't really model it as much as rely on a sequence of actions to happen. So you make the request, and then that fires off. And while it's still in flight, you modify a DOM element to show a spinner. You make the spinner visible. And then when the request comes back, you hide the spinner and you set the value. So you do everything in an imperative way, right? And this works out for a lot of cases where, a lot of paths that could happen. But it doesn't completely capture it, and it doesn't allow you to reason at a higher level about it. Like, for instance, if you have multiple things you're waiting on, now it's like, I don't know what to do anymore. So what if we modeled this thing as a value, the whole state? And so you could draw out the timeline. Okay, the value is like uninitialized. It's unrequested yet. It's like undefined, unknown, whatever you want, however you want to call it. It's like this initial state where you don't have the value yet, but you haven't even started looking for it yet. Okay, then you make, then you realize you need that value. Okay, and so you're going to transition to a new state, which is like a loading state. Okay, and so then the request comes back. Now it either succeeds or it fails. Okay, let's say those are the two options. So you need to have a state that for each of those that it transitions to. If it succeeds, boom, you can store the value in some state saying that you got it, you're ready to show the value, you don't need to show loading anymore. And if it failed, you might have some other thing like we're going to retry 3 times. You got to keep track of that state. But notice this is also an algebra, because you can look at every state that the value could be in, and you could look at every possible event that could happen to it. So we could make another request, right? And so what's interesting is you could have these cases that show up in your web app and you just haven't even thought of. For instance, what if we make the request but we already have a value? What state do we transition to? Looking at it algebraically and seeing that there's all these states and there's all these events, you have to multiply them out and see what to do in each possible case. But when you do that, you create a kind of algebra that composes this value with the events that could happen to it. So the events that could happen to it are: I initiate a request, I get a positive, successful response back, or I get an error back. These are all possible. These are all possible transitions, and so you need to have a system that, a state that like works for any possible transition, right? And yes, it's a combination of current state and a result. It gives you a current state. It's not a monoid because the result or that event is not the same type as the current state. You might be able to finagle it so that it is the same type, and then you have a monoid. But I think it's best not to try that. Just leave it as current state and event gives you the next current state. Okay, so when I wrote these out and came up with the examples, it was very clear to me that there were some principles going on here. So I want to share those. One principle is that the combining forms are simple. They're very easy to write. Often, if you start by modeling let's say in a classical OO way, you might model the video editor, and you have some operation that's like add frames to a video, right? And so you're first of all, you're mutating stuff, so that's kind of already complex. But you get into like weird corner cases, like adding to the video is going to change the length, and what if something comes after it? You just have this weird, all these things to keep track of, right? Whereas in the algebra way, it's much clearer how the things should combine. You create this unified abstraction of clip, and it has a length, and it's just a function of time to image, to frame. And the combinations that you can do, because it's such a limited abstraction, there's not much you can do with it. And that constrains you into coming up with these simple combining forms. They have a minimum of concepts. Remember with this video editor, we just had clips, and then we had a few operations like sequence overlay, left trim, right trim. We came up with like empty clip. There's like a minimum of concepts to put together. The same with the parser combinators. You start with a basic one character matcher. You also have a matcher that doesn't consume input but always succeeds. You probably have one that doesn't consume input but always fails. And then you have these operations to combine them. The final thing is this idea of whole values. To me, it's kind of like this ineffable principle. It's very hard to describe what it means. I have a whole episode trying to explore this idea. This is one of John Hughes's ideas. He's a big, functional programming kind of, I don't know what you call him, researcher. And he has this notion of whole values, which basically means you have everything you need in the value to make a decision, make a computation from it. Often when we're programming, we will separate the values we need into different variables, right? We'll have this piece here, this piece here, this piece here. And it's great. It works great for this one algorithm we've got, right? But if you put them all together into a single value, then that value could become useful in its own right. It's got all the context it needs around it to make useful decisions, to do useful computations. Okay, that's all I got, so I'm going to recap. I went over the 3 levels of thinking. Again, this is just a scheme I'm coming up with to organize my teachings and stuff. I don't know if it has any real, only anecdotally do I have any sense that this is real, right? That is really how people progress while they're learning functional programming. I got this question in the comment about examples, and so the 3 examples I came up with are a video editing algebra, a parser combinator library, and this asynchronous value that's kind of like a state machine. And then I went over 3 principles. Simple combining form. So we talked about the different forms are very easy to write. A few lines each. A minimum of concepts. So we could have added other interesting concepts to the video algebra. But notice, instead of coming up with like a cut clip operation, I decided to turn it into 2 operations. One is trim from the left and one is trim from the right. And with those 2, you've kind of broken it down more. Each one is easier to write. And so you kind of have a more minimum notion of of the pieces that you need. And then the whole values, which is that ineffable idea that when you put stuff that goes together, it has a strong relationship that it really is very cohesive. It contains its own context and can be useful outside of that little piece of the algorithm. that you're writing right now. Okay, if you like this episode, you can find this and all past and future episodes at lispcast.com/podcast. You'll also find links to subscribe. Every episode has video, audio, and text, depending on how you prefer at that time to consume. And then also on the pages, you'll find links to my email and social media. I love to get into discussions. I love reading the comments and the questions that I get on Twitter and even in the YouTube comments. So thank you very much, and rock on.